very on time. Time to start. Okay, distinguished guests, friends from all over the world joining us through our online streaming. Ladies and gentlemen, good afternoon. Welcome to this afternoon's forum. Our topic is AI applications in reservoir management and safety monitoring. What perfect timing for today's forum. Extreme weather is no longer something rare. It has become the new normal for water resource management. We would like to express our heartfelt thanks to the government, the Water Resources Agency, and all the experts here with us today for your continued efforts in protecting people's life and property. Today, we are grateful to have 3 experts sharing their essential knowledge. We are anticipating a fruitful afternoon. It's our great honor to invite the Deputy Chief Engineer, Zhao Qingzhen, to deliver the opening remarks. Let's give a warm welcome to our moderator, Deputy Chief Engineer, Mr. Zhang. Come to the stage. Welcome.
罗教授、王教授和我们张教授3位教授，今天与会的贵宾，来参加这个 AI 水库管理与水利监测的这个论坛的好朋友，大家午安哦。
Distinguished guests, ladies and gentlemen, welcome to this forum. It's a great honor for us to talk about AI in reservoir management. In our daily life, AI is very common, but in the past, when we didn't have AI about 40 years ago, we did not have AI. Feichui Reservoir, I was working for protecting the safety of the Feichui Reservoir. Whenever there was a natural disaster, we have to go around the reservoir to collect data, including the soil and the water volume. And then we will draw the map and draw the drawing for analysis of the data to ensure that the dam or the reservoir is safe. So I also work for the Taipei City government as an expert for monitoring flood. We often have to visit the mountain area to collect data on water level. And again, once we collect all the data, we can analyze the data to check the intensity of the water. And everything is done manually for the hydrographic analysis. So you can imagine it's very time-consuming. And we did not have cell phone at that time. That was the time when we did not have AI. That was 30 years ago. And we also have other approaches for the full hydrographic analysis. And usually we'll need a team of 70 people in order to monitor the flow speed, the velocity, the water level, and so on. We also need to monitor the peak flow, and everything is done manually. But today, when we have a reservoir that plans to discharge, we don't really need to worry about the water level in the bottom level, because we now have AI to help us. And then 20 years ago, I worked for Shimen Reservoir. I was also responsible for the operation of the reservoir. At that time, the capacity of the reservoir was not very good. it's about 10 million tons of water. And before the typhoon season, we carry out projects to improve our capacity because the water capacity in the reservoir was not enough to cover all the domestic need. Again, we have to calculate the water usage and the water demand as well as the reserve water all manually. We also need to think about the water usage in different counties and cities. But now, with AI, with smart management, we can manage the water more efficiently, and we can allocate the water resources more intelligently. Shimen Reservoir is very famous because we have come up with 5 principles of water usage. We have different inlet of water for water demand. So certain inlets are reserved for the high altitude area, and other inlets are reserved for the farmland. And water that has been used for hydropower can again be recycled for domestic use. So all these 5 principles are very simple, but they are all empirical and they are experience-based. But of course, it's just a rough principle. Now with AI, we can have better management of the reservoir, and we can have better efficiency. So these are my past experience, and I believe that our experts will share their expertise about how to apply AI in reservoir management. And Professor Luo will be introducing our speakers. It's just a great pity that our experts from the Bureau of Reclamation could not attend in person. It was a great pity. So that concludes my welcome remark. Thank you.
Motorcycle is our best friends always. Thank you, motorcycle. Okay, next let's give a warm welcome to our moderator, Chief Secretary Wei Chen-Ro, come to the stage. Welcome.
简副总、那张主任跟
Deputy Chief Engineer Jian and distinguished guests and distinguished professors, as well as our friends that we have been worked together. Good afternoon. And I know Deputy Chief Jian has reported that the purpose of our today's event is to bring us the newest knowledge internationally. And I'm so happy to see you here in this section. And we have 2 parts for this section. So in the first section, we have 1 speaker, and in the second part, we also have 2 speakers. And as mentioned, our first speaker is an expert from USBR. And he couldn't be here in person, but he's actually online. And let us say hi to him.
So I know you are online right now. So I know you needed to keep the silence due to the U.S. government budget cut. So we are very regret you cannot be here. But we greatly appreciate your recording your valuable speech for us. So right now I am going to introduce you to our audience. Cameron is the well-known civil engineer in the U.S. Bureau of the Reclamation. He got his master's degree from the UC Davis, and he also holds the dual bachelor degree from the civil and environmental engineering from the University of the Michigan. I think I hope I remember this. So Cameron expertise range from the dam safety, hydraulic modeling, and the safety, the safety issue for the hydraulic structures. So he developed a very useful tool for the risk assessment and I think the measurement for the dam safety. So let us give a warm welcome for his recording speech.
Hello, thank you for having me here today. My name is Cameron Carpenter. I work with the U.S. Bureau of Reclamation. It's a pleasure to be able to present to you all today. I want to thank the Taiwan Water Resources Agency for having me. I apologize I cannot be there in person, but hopefully you find this all valuable. I will be presenting on using artificial intelligence and machine learning to screen dams for seismic risk. Quickly, like I said, I work for the Bureau of Reclamation. We are a bureau under the Department of the Interior, whose mission is to manage, develop, protect water and related resources in an environmentally and economic manner. We primarily work in the 17 Western United States, and we were founded in 1902 to help deliver water to the West. Interesting fact about us, we are the largest wholesaler of water in the United States, as well as the second largest producer of hydroelectric energy. Quickly to touch on our inventory, we have roughly 300 reservoirs impounded by almost 500 dams. We have 53 hydroelectric power plants, approximately 10,000 miles of irrigation canals, and also roughly 250 recreation areas. Here I show a map of all of our high hazard potential dams. These are dams that, if failed, would likely lead to loss of at least one life, as well as all of our hydropower facilities. I quickly wanted to mention the team I work with, the Dam Safety Office. Here is some interesting information about our group. As I mentioned, we have roughly 500 dams. A little over 350 of those are these high hazard potential dams. Our office is responsible for running the projects to make sure they stay within our guidelines, and we are comfortable with the risks we have. Quickly, some things of interest. Our current projects we have going on are estimated to bring in upwards of $2 billion of value. We currently have 17 projects currently being worked on. This will benefit 9 different states, as well as make right around 400,000 people safer, allows to irrigate 5 million acres of land still, and benefit over 20 million people. Going more into our discussion of today, here's a map of all of the reclamation dams plotted with active faults found by the USGS. And as you can see, many of our dams are located in heavily faulted and very seismically active areas, especially along the western coast of the United States, where we have both the San Andreas Fault as well as the Cascadia subduction zone, which both pose significant earthquake risks to our facilities. Just wanting to tie that a bit into Taiwan. Obviously, it's also a very highly seismically active area. sitting at the convergence of the Eurasian and Philippine sea plates, which lends itself to frequent earthquakes. And you can see here this faulting map produced by the Central Geological Survey of Taiwan, showing many of these faults along the western and eastern shore. And you can see here this map of some of the larger dams in Taiwan and how many of these dams do line up with this active faulting. To go back to reclamation, some of our major factors that go into our seismic risk are the construction methods of hydraulic fill, which were used in some of the early days of the construction of our dams. However, these have mostly been addressed over time. As I mentioned, we do have these very seismically active areas and these substantial risks drivers, such as the Cascadia subduction zone and the San Andreas fault. And we have found over time that with developing technologies such as LiDAR and detailed satellite imagery, our scientists are finding more and more faults that were previously unknown, and that is leading to us finding increasing seismic loading and therefore seismic risk to our facilities. And why do we care about all this? Obviously, we can have the seismic failure of dams. I have two well-known cases here shown on the screen. But seismic failure is the collapse or breach of a dam due to earthquake-induced forces. It leads to an uncontrolled release of water with usually little to no warning time, which is different than most hydrologic risks, which can be forecasted, or static failure risks, which generally are much more slowly developing. The common mechanisms that cause this are usually ground shaking induced cracking, foundation instability, or liquefaction of embankment materials. We will primarily be focusing on the liquefaction of embankment materials. Next, we need to understand what tools we have actually to understand our seismic risk. So we can go out and do geotechnical investigations, look at trenching to understand the faults better, where we can then go update our loadings using seismic hazard analyses. Next, we have numerical modeling software such as FLAC2D, or we have numerical tools or numerical models such as the Idris-Bullinger methods or the Seaton-Idris simplified procedure. Today, we'll mostly be focusing in our case studies on these latter 2 points, the numerical modeling and our numerical tools or models. So getting into the 2 case studies, we will first be looking at the reevaluating of the Idris-Bullinger 2010 study that they did, and if we can recreate this using machine learning. And then we'll be looking at the screening of dams using machine learning and looking at if we can model deformation in a way to better understand our deformation risk at predetermined events. So first, we'll be looking at Idris-Bullinger 2010. This paper presented an updated framework for evaluating the potential for soil liquefaction using the standard penetration test. It redefines the stress-based approach by incorporating an expanded case history database, re-examining key parameters like overburden corrections and magnitude scaling, and introducing a probabilistic model for liquefaction triggering. So, just to give some of the things that went into the study, they looked at 2 main ways that there could be, or 2 main factors contributing to liquefaction. This is the corrected blow count. A blow count is a physical test performed in the field on the soil that results in a measure of how much resistance the soil can withstand before failing. The corrected blow count means that the test was corrected to normalize the value for various factors such as the depth of the test, the type of device used in testing, and as well as some others. The other factor is the adjusted cyclic stress ratio. The cyclic stress ratio value is a measure of how much force will be applied to the soil at different depths during a seismic event. The adjusted cyclic stress ratio means that the values were adjusted for factors such as the magnitude of an earthquake. Here on the right side of the screen, you can see the results of the Idris-Bollinger study. Here we show the trend they found for a 50% prediction, or that you have a 50% likelihood of the soil liquefying. These red dots on the screen are cases where the soil did liquefy, whereas green, there was no liquefaction that occurred. So we decided to see if we could recreate this using machine learning. So two approaches were taken in the data we used. We looked at using all of the inputs that they also were looking at, regularization to help figure out what might matter less in these studies. Really, that means that our models could more or less turn down the coefficients of how much these inputs would be affecting our model, all the way down to the point of being zero, where they're essentially ignored in the model. The other method for the data we looked at was crowdsourced answers from the geotechnical industry, primarily experts that work at reclamation. And generally speaking, we arrived at the same conclusion that Idris and Bollinger did as well, where we only used the equivalent cyclic stress ratio as well as the corrected blow count, since these are the two features accepted to estimate liquefaction across the industry. Next, I want to briefly touch on the three different types of models that we looked at. The first being a support vector machine. This can be used for both classification and regression. It looks to find the ideal hyperplane that can separate the classes with the maximum margin. It's very useful for high dimensional spaces and can handle both nonlinear and linear boundaries. However, it can be quite difficult to interpret. The next is a logistic regression model. It is used exclusively for binary classifications, and it can estimate or give you an equation for any threshold value you want. We will be focusing on the 50th percentile, as we showed before. It is very quick, it is very interpretable, and works well when there's a very obvious trend or a easily quantifiable trend. And finally, we'll be looking at neural networks, which are very flexible and capable of modeling complex nonlinear relationships. They consist of layers of interconnected nodes or neurons, hence the neural network, that learn representations of the data to interpret and then provide results. They can be very complex, take a while to be generated, but generally produce very good results. Finally, before we get into some of our model results, I want to look at how we will actually be addressing these. First, looking at the score values we have here, we can be looking at our data in terms of true positive, which are our correct guesses, our true negative, which are our correct guesses, but saying that things would not liquefy, our false negatives, which are cases where the soil would liquefy, but we estimated that it wouldn't, and then our false positives, where we believe there could be liquefaction, but in the field it would not have. Then, using those, we can look at either error, which is the number of false positives and false negatives divided by the total number of results we got, where lower scores are better. Recall, which is our true positives, plus our true positives and false negatives, which gets higher, better. And then we also looked at receiver operating characteristic curves, which looks at the true positives versus the false positives. This can produce these charts like you see here. Usually the way you look at this is a line from 0 to 1 here is a random guess. You always want your model to be performing above this line to show that it does have a better understanding than random decisions being made. And then we can look at the area under this curve. If it is above 0.5, that's better than a random guess, as I mentioned. And a perfect model would look like we have this line here and have an area under the curve of 1. So now that we've defined how we're going to look at our models, we can look at some of the results. The main takeaways from these results are that we generally could outperform the Idrison-Bollinger results as far as these metrics go, and in some cases by quite a bit. We see that both of the logistic regression and the neural network with 2 inputs generally outperformed it, as well as the neural network with all inputs. And then I do want to also point out, when we were considering what we want to be the most important metric that we have, we consider this to be recall, since we would prefer to never have any false negatives, because that would generally be, or having liquefied soil in our dams is much more catastrophic than, generally speaking, just having any sort of error whatsoever. And so we want to minimize our false positives, or our false negatives, excuse me. Next, looking at our ROC curves, I have these split into 2, one with all inputs, and then one with just the 2 inputs, the cyclic stress ratio, as well as the corrected flow count. You can see that for all inputs, the neural network performed the best. And for the 2 inputs, we had the also had the neural network perform the best. However, it was very similar to the performance of the logistic regression model. And you can see that in almost all cases, the our models were outperforming the Idris-Bollinger equation from 2010. Finally, we wanted to look at this in a more engineering sense. And so we plotted all these up, looking at the cyclic stress ratio and the corrected blow count, and seeing how the actual relationships performed. From this, you can really see that the logistic regression and the support vector machine model produce results that are not engineeringly viable, with them bending backwards or having multiple points that they could produce for a similar corrected blow count, which would not really be a true function. However, our neural network model very similarly followed the Idrison-Bollinger results, showing that we can, looking at these in a way, in an engineering perspective, will give us better results than a just data science manner, and that we can't just trust maybe our assessment metrics. We should always have our machine learning models being reviewed by subject matter experts as well, so that we can have a better idea of how everything's actually functioning. Moving on to my second case study, this is trying to evaluate the amount of deformation that a dam may experience under certain events. as I mentioned before, we have many tools for understanding our seismic risk. But one of those major steps is numerical modeling. We can get all of our loads, but when it's time for us to try to estimate deformation at reclamation, we generally do this in FLAC2D, on which I will be talking a little bit more about on the next slide. However, these models can take quite a bit of effort to set up, depending on the level of our work or the level of the design we're looking at, whether it's looking at an existing condition, just as initial gut check, all the way up to developing models to evaluate a final design. It can take anywhere from 20 to 100 staff days to complete the modeling process, including checking all of this. And so if we can develop a screening tool, we can save many staff days and a lot of staff time as long as it can produce good results. Just to dive in a little bit more about FLAC2D, it is it stands for Fast Lagrangian Analysis of Continua in 2 dimensions. And it is a numerical modeling software based on the finite difference method. There are many things that, or many methods that can be used to model the soil strength in this. We just looked at models that used more clone. And then some things that we wanted to mention is that it cannot model 3D effects, which can affect the stability. And additionally, it can actually look at the seismic induced deformation or crest settlement, hence why we use it for this. I also just quickly want to talk about some minor differences in the different machine learning methods we looked at. As I mentioned before, we used support vector machine. A subcategory of this is support vector regression. That's kind of what's being depicted here on the right side. There are multiple different ways you can look at it, using a linear fashion, like here in the middle, or using nonlinear kernels, such as a polynomial or an RFB. Then, similarly to our last one, we could look at a linear regression, or in this case, we actually looked at a ridge regression model. Because of the number of inputs we had, we wanted a way to really help regularize the bias which ridge models allow. This is kind of the idea behind them, is that you'll be looking for the optimum point where you minimize the bias and also the variance of your results. And again, we will also be using a neural network, which we talked about before. So our inputs that we used were the dam geometry and soil parameters, including how much of if there was a cutoff wall installed, and if so, the width, the strength of the core, the size of the core, the size and strength of the shells, the phreatic surface, as well as any information to do with stability berms, and any other soil data that we could get. We also included the earthquake parameters, and then we were going to try to model, our target parameter was the effective displacement. So we weren't looking just at the center line, we were looking at the total loss in crest elevation. Finally, just to touch on our inputs one last time, we took these from about 550 FLAC2D models. We only use models, as I mentioned before, that use the more clone soil method for soil strength. So we did not look at things that are some of the newer tools, such as PM4 sands or PM4 silt. The models were a mixture of dams in their current conditions, as well as some proposed modifications to dams. The return period that we looked at was all the way from a 1,000 year to a 100,000 year earthquake event. So a big range there. We only use models that were deemed to be of high quality by our reclamation experts. And then finally, we did save 20% of our data to be used in testing at the end once the models were trained. So to look at some of the results from this, just to start to point to the overall performance of the models, here we're looking at mean squared error, and this would all be in square feet since we were looking at deformation. The neural network outperformed the rest of the models quite considerably, with the ridge regression and the support vector regression being quite similar. Here we have a chart showing the FLAC2D values estimated in the or estimated deformation, as well as our predicted deformation from the model results. This red line would indicate perfect matching. Some main takeaways from this is that the support vector regression model generally predicted a very similar amount of deformation, kind of despite what the inputs were, and very much differ from our finite differential models. And the ridge regression and neural network models generally produce much more realistic results. However, the ridge regression model had some major outliers, especially once we got to the lower end of the deformation that would be believed to occur. Looking at these results in one more way, we have the residuals here, so the difference between the calculated values from FLAC2D, and then we subtract out the predicted from our machine learning models. It shows very much the same story, but in a different sense, where as the predicted FLAC deformation increased, we see an increase in the support vector regression models, and then we generally see pretty good performance of the other two, except in the case where the regression model had some really substantial outliers, which included the height crest increases substantially, which is obviously not possible. So overall, we considered the neural network to provide the best results, and generally speaking, some very realistic results as far as the screen level tool. So our main takeaway from this case study is that we can successfully estimate the effect of deformation being produced by our FLAC2D models using machine learning. And it can be the neural network did very well and outperformed the other models in terms of mean squared error, but that was primarily due to the major outliers from the ridge regression model, which could also be a really good tool. That being said, as far as a neural network goes, it did not take that long to train. It was only about 30 minutes, and as I mentioned, provided very good results, which could potentially be used as a screening tool to help save staff days. I do want to caveat some of our work on this, that we used a very small data set, a total of 550-ish model runs is not that much for training machine learning tools. And due to the scrutiny that we want to put into the inputs and the outputs, it's difficult to find that many high-quality FLAC2D models to add to our data set. Additionally, I want to point out that we were only looking at one type of soil strength model, which is also limiting our input pool. So my conclusions are from our first case study that we can produce similar results to the accepted technical solutions, and in this case for liquefaction triggering, but even with some improved performance metrics. And then from our second case study is that a neural network was able to produce similar deformation results as a FLAC2D model was, while requiring just minutes rather than multiple staff days. And it definitely has a lot of potential as a screening level tool when it comes to doing analysis. And my final conclusion is that human input is really important to this process. You can't just throw data in and hope to get out valuable data at the end. Getting expert opinions on what would actually be useful as input data is really important. And then also having those experts look at your results to make sure you don't have things that do not make any engineering sense or could not be considered true trends. So with that, I want to thank everyone for listening to my presentation today. I wish I was there in person, but I greatly appreciate your time and hopefully you found this valuable. My contact information is here on the screen. I hope to hopefully one day be able to work with everyone here, and I really appreciate your time. Thank you so much and have a wonderful day.
Okay, so Cameron, so many thanks for your fantastic and inspiring talk. So I sincerely hope we can see you in person next year. 我想因为就没办法提问了，因为他就没办法。
Since we couldn't raise questions, it's a pity. But in the afternoon, we have the panel discussion. And originally, we had 2 speakers for this session. And our next speaker is Professor Zhang Liqiu of Tangang University. You can see her bio on our information brochure. But we know that Professor Zhang is a distinguished scholar in Taiwan. Internationally, she is listed as one of the most influential scholars in the world by Stanford University, especially in the area of hydrology and geoscience. And another example, a couple of years ago, I started to take in our administrative job, and I visited Malaysia to recruit students. I met a senior who asked me if I have heard Professor Zhang Liqiu before, because her study and her research project has been quoted and used in Malaysia. So you can see that internationally, she is well known and distinguished. Also in Taiwan, we all know that in Taiwan, the most important governmental agency for research is National Science Council. And for the flood management division, if you can be the reviewer for that division, you will be known as one of the most distinguished scholars, and she's actually the division chief. So she's my boss, basically. So I'm humbled to introduce her. And now, without further ado, we are going to invite Professor Zhang Liqiu to come up to the stage to give her presentation. Thank you very much for your kind introduction. Generally speaking, we are just researchers who focus on our own research project. And originally, I prepared the presentation in English. And we know that in recent years, people are promoting the application of AI. But if I reflect on the past, I feel like I am a missionary I am promoting this concept, and so that more and more people are applying AI in their field. And I hope that my presentation will be useful for you. Why do we want to talk about this topic? Because for scholars, we focus on forecasting flood peak. But in fact, if you are operators of reservoir, when you experience typhoon, you really wanted to know the full hydrography because that feels reassuring. You know when the water level will rise, you know when it will reach the peak, and you know when recession will occur. And this is really important for us. So if you are the operator sitting in the control room during a typhoon season, what kind of information do you need? You will need to know at least 3 elements. The first, you want to get a complete flood picture, which includes the entire flood event. It's not just about the peak, but also the initial rise, the timing of the peak, and also the recession. This will help a lot because you can make your decisions early and you know when to discharge water in the reservoir. And also it can help ensure safety for the downstream area because you know when to discharge the water and you can notify them early. And secondly, you also know when you should store the water because you need to get the timing right for the best result. So the full hydrograph is really important for our forecasting. Then why do we find it challenging? I will talk about all these challenges we face. First, it's always very difficult to forecast the water rise and the peak, not to mention the recession. These are my own feelings, but usually we have difficulty when the rainfall stops. The AI model will not work that well because the flow has slowed down. The rainfall has stopped, but the flow is there. So how can we continue to calculate the water? They are groundwater, and we also need to think about the surface water. So a lot of models find it challenging to calculate these numbers. They can calculate the peak, but when there are problems with the inflow, they will face difficulties. So we need to know. What we wanted to know is when should we discharge water and how much water should we store. And these are not linear. So that means the current model is not working for us. So I work with Shimen Reservoir for over a decade. I think it's the 13th year that we collaborated. And I have used AI to help support the real operation of Shimen Reservoir. And of course, when we first began, my thinking and my mindset was different from now on. And I think that's the bridge that we have built to fill the gap. We wanted to make sure that the data is physically interpretable and we can provide real-time data and visualization, which is very common today, but not that common a decade ago. Thirdly, I also wanted to help Shimen Reservoir train their experts. So I'm not just training AI, I'm also training the AI experts and professionals. And lastly, we need the actual operation to bridge the gap. So it will be mutually beneficial if we can have the research and the real operation together. And this is my research objective, which is very clear. We want to develop a full hydrograph. For example, we will know the forecast before the flood. We can also think about the water storage after the flood. So it's not just for 2 to 3 days. Instead, it may last for a week. And such full hydrograph forecast is not just one picture. It should be able to support decision making. If you have managed reservoir or been involved in reservoir work, you will know this graph very well because we have the pre-typhoon stage, the pre-peak stage, and the post-peak stage. In the past, when I work with Shimen Reservoir, they asked me if it's possible for me to provide them with all the data. Because in the past, what we did is we provide them with the data in real time. But you see the 2 lines here? And a lot of times, a lot of research paper stops here. They will not continue forecasting if the rainfall has stopped. And they will think that the number is not enough to continue to forecast. And I always wonder, why do we stop? Does it mean that we no longer have the risk? So a lot of research projects will stop there. But the reservoir really wanted to pay attention to this information because it will affect their discharge time. So as a researcher, we only focus on 3 days for the flood forecasting. But for operators, they will need at least a full week. They hope that when we provide them with the forecasting data, we can provide them with a week of data. So I started to carry out research. I use AI to predict the peak. It did quite well. So we know that AI does very well for water rising and peak. But for recession, it didn't do that well. So we finally found a solution, which is the storage function. A lot of you are very familiar with it. We know that during the peak, the storage function could not perform very well. But when the rainfall stops, the reservoir becomes like a storage basin. So you can use storage function. And so that means it's very suitable for the recession phase. And we can combine the 2 models together to make it into a hybrid model. So as you can see on this slide, let's talk about RNRAX, or I call it NUX. NUX is an AI component. It's an RNA model. It is very good for the rise and for the peak estimation because the inputs are related to the rainfall. And once the rainfall stops, the input stops. And so they will drop to zero when rainfall stops. So you can see that NUX is really good in modeling fast flow changes. So when you see increasing water level and peak, it's very good for estimation. So its strength is high accuracy during intense rainfall events. Whenever there is rainfall, its accuracy is very good. It can capture rapid flow increases very effectively. But how about its limitations? Its limitation is whenever the rainfall stops, all AI model, not just NUX, whenever the rainfall stopped, they could not provide us with accurate estimation because their influence factor disappeared and they could not estimate the recession flow. And you will get the wrong impression that the peak is going down so you can discharge water, which is a wrong decision. And the next model is the storage function. A lot of you are very familiar with this. Basically, we only use two parameters. So the first is water storage. And we can capture the watershed storage characteristics. And we know that when you have high storage and when you have low storage, you can decide when to discharge water. So basically, a lot of Japanese use this model to decide when to discharge water. And it's physically interpretable. And also, there is a simple calibration. That's why it has been widely applied. But there are also limitations. It's very similar. The strength of the storage function model is that during the recession phase, it has excellent performance. It can also accurately simulate gradual flow decline. And if you use this model, you will not have any problem to reflect the catchment storage. But if you use AI model, you will need to be very careful. But the limitation is it usually it's not very accurate during the early rising phase. And it cannot capture the intense rainfall. Again, because it's more like a storage model, it's not for the intense rainfall. So we know that NUX is very good for the rising level and the peak level, but storage function model works well for the recession. So they can be mutually complementary. And so we can see if we can put them together. But how do we do that?
So we need to find a transition point. So here, we mainly rely on the rainfall because facing typhoon, the rainfall is estimated, and we don't know what is the amount of inflow. We don't have other data. But now, to do the transition, we need to calculate the rainfall, the peak, and we rely on the forecast. So how to switch is that when the rainfall lowers than a certain threshold, then the whole system will switch and start to think, okay, now it's time to discharge. So it's time when we use the storage function. That's the most important transition criteria. And next, it's about the peak, because different peak has different discharging timing. When the peak is really high, when the rainfall is really high, sometimes it starts to discharge, and the threshold of rainfall is higher. But when the peak is lower, then the number is lower. And how do we find the right peak? Do you still remember what RNOx is good at? So we can actually leverage RNOx to estimate when the peak would happen. So we have the peak data. We also have the data of rainfall. So we know how to switch our models. We don't need to rely on our operator to decide when to switch. It can switch automatically based on these two numbers. And this is Shimen Reservoir. And Shimen is really important. In Taiwan, we have known this because the downstream of Shimen is a very prosperous area in Taiwan. So the safety and health of Shimen is very important. And we also rely on Shimen Reservoir to supply water. It needs to storage at least 4 or 5 times so that we will have a full capacity. That is why a good estimation and forecast is very important. And it will be perfect for operators to make their decisions. And on the slide, as you can see, this is the data collected in 2016 about Maggie typhoon. And if we look at the left photo, if we only using RNOx, as you can see, when the rain stopped, then the forecast decreased to 0 fast. And as you can see on the left side of the graph, when it started to rise, the number was really precise. And on the right side, if we use the storage function, this is what we got. And sometimes it rises too fast. The estimation about the rising was not accurate. And as you can see, when it started to recess, the number was quite accurate. So you know the advantage of two models. And next, we combine these two models. When rising and peak, we use RNOx. And when it's about to recess, we use storage function. So this is the forecast that we have. And you still remember, we only rely on 2 data, and that is the flow and the rainfall. And on the slide, we actually put the 3 forecasts together so we can have a better comparison. So the first one is RNOx. But then we can see, okay, so RNOx is really good at left, but on the right side, the place that I circle was not that accurate. And because the bias that we have in the beginning, that is why they have bias and error in the end. And next, if we can have a better forecast and prediction about one typhoon, what about other typhoon? We actually have done 82 tests, and these are some examples. So as you can see, this is a intense model. Okay, so I couldn't see it quite clearly here. And this is the data from Typhoon Sula. And as you can see, the estimation were pretty good. And the 2 graphs that I put on the right side are from Nari Typhoon. And it actually has 2 peaks. And as you can see, RNOx actually dropped in the middle and then climb again. But then on the bottom side, the data, the estimation that we do for Kaimi typhoon. And as you can see, because the rainfall was not that much, it actually dropped in the middle. But because we are now having two models combining together, so when they start to recess, our storage function came out. And this is our data. And as you can see, these indexes were all pretty precise. So lastly, what can we have from our research? First of all, we can have a longer extended lead time. And based on the time, we will have abundant time to make our decisions, to make our plan, to inform our downstream operators, tell them what kind of situation they will be expecting. So this is one benefit. And secondly is we can optimize our discharge. And since we have better prediction, then we can have a better discharge. And to know where the risks will be. And lastly, we can have a safer refill. We know when to refill our reservoir. And this is what Taiwan's reservoir operator would like to know. And the conclusion is, as you can see on the slide, so in the beginning, when it starts to rise, so we actually have 3 stages. So in the pre-peak stage, if we have the better forecast, then we can have a better planning. We know when to discharge. And at peak stage, we can ensure downstream safety. And lastly, at post-peak stage, we can refill our reservoir. We can have a better capacity of reservoir. So lastly, it's not about a competition between AI and traditional model. We can actually have these 2 types of model working together. And this is not just an academic model research. The research can actually benefit our application and operation. And operation can also benefit research by bringing more challenges. And I think the most important thing is that our research and our operation need to provide a data that is valuable for our operators. Thank you. So thank you, Professor Zhang, for your amazing AI estimated keynote speech. And I know AI is very important. It can bring data. And she actually mentioned 3 stages about AI, and the most important stage is about the data of AI. And I think for us, when we look at the AI magazine, they always talk about what type of data the AI has brought is the most precise, and that is customers' consumption pattern. When knowing the pattern, we know when customer would like to buy things. But about hydrology is really difficult. Why is that? Because our geographical condition would change. So the past data sometimes will be biased. So how can we have such accurate result? I think it's really difficult. Because the past data might not be suitable for modern times usage. And I just forgot to mention one thing, and we all know Professor Zhang is from the Department of Environmental Protection and Water Resources. And one day I was reviewing the project for Ministry of Education. And one day I saw Professor Zhang's name on one project. And I was quite surprised because Professor Zhang is so versatile. She's so good at many different disciplines. So this is pretty much the end about our first section. So I would like to know, so maybe do we need to have an extended refreshment time. And because we are a little bit late, and in the afternoon in the second session we only have one keynote speech, so we actually still have time to take a short break. So let us have 20 minutes tea break.
So everybody can stay in your seat. Okay. I need your finger. Give me a heart gesture. Yeah. Everyone, please look the stage. And your finger, heart, or your big finger. Oh, 1, 2, 3, smile. Again, 1, 2, 3, smile. Okay, thank you. Okay, now take a short break. We will begin at 3 o'clock 20. Okay, 3 o'clock 20. And we have prepared some refreshments for everyone, so please help yourself. And if you need a restaurant, the restaurant is just outside this room, maybe on your right hand side or left hand side. Thank you. Okay, everybody, welcome back to our forum. Next, let's give a warm welcome to our moderator, Chief Secretary Hui Chunrou. Come to the stage. Welcome.
好，谢谢大家又回来我们这个 section 那
Thank you very much for coming back. In this session, we have one speaker, Professor Wang Liben from National Taiwan University, and he is going to talk about AI in hydrometeorological applications. I thought about my supervisors in the US, and I wanted to endorse them because both of them received the Nobel Prize in the hydrology area. Both of them told me, Wei Chen, you know, if you look at all the hydrological related books, you know, hydrology include groundwater, surface water, and ocean. And if you pay attention, you will know that most people carry out study on surface water. And how about the second largest? Probably groundwater? Yes. Do you know why? That about 70 to 80% focus on surface water, and groundwater only has about 20% or less, because it covers a lot of different disciplines. And the least one is the meteorological or atmospheric water. This is the most challenging discipline in hydrology field. And so most researchers did not carry out research in the atmospheric water. And Professor Wang is an exception. He has chosen a very difficult field in the hydrology field. In fact, I met him for the first time today. And so I wondered how I should introduce him. But I have reviewed a lot of projects, and I have seen his project before. As a scholar, as a researcher, it is very important to be down to earth. And I remember when I reviewed his project, I feel that he was really down to earth. We often have the impression that European and American scholars are more advanced than us. But in fact, Professor Wang's research is really advanced. And he has collaborated with Empirical College. We all know that Empirical College and also UV Leuven are both distinguished universities. So I believe that his projects are worthwhile. And so we can see that he's also a very distinguished scholar in our field. Let's welcome Professor Wang. First of all, thank you very much for the kind introduction. I'm very honored to be here with and to see so many distinguished scholars. I came back to Taiwan a couple of years ago. And our topic today is actually reservoir safety. But my study is a bit higher. It's way up in the sky. So we really hope that we can study more about rainfall so that it can have better application in hydrology. And I'm going to skip this part because our moderator has kindly introduced me. My talk will focus on the 3 parts. I'm a bit different from Professor Zhang. She has described her study in very detail. But what I wanted to talk about is what our team has been doing and how we have been using AI and our thinking behind applying AI. So my talk will first talk about AI in nowcasting for the short-term and intensive rainfall. And what is AI really good for? Secondly, I will talk about AI's power of learning spatial and temporal features. And thirdly, can we teach AI to say, I don't know? Because if AI doesn't really know the answer, it shouldn't give you a wrong answer. It should tell you that he doesn't know and why he doesn't know. And now let's talk about nowcasting, especially nowcasting of torrential and intensive rain. A couple of years ago, when I was in the UK, I was involved in projects related to the application of AI for urban flooding. And we decided to try to use the AI to help us predict flood-prone area in Birmingham. And the AI that we used was quite good, quite accurate. So I saw its potential. And I decided that we should move upstream for the nowcasting. And nowcasting is usually used for the radar rainfall or for the mathematic models. Usually it can have a pretty good result. That's what your cell phone tells you, that it's about to rain in 2 to 3 hours. But at the very beginning, its performance was not very good. And secondly, for the atmospheric model, usually the course is too long. And for the city, it's not enough. And the lead time is not enough. So we will need to use radar rainfall image to support. And you don't need to go into the computer to run the data to get the result. But usually the forecast is less than 6 hours.
So about nowcasting, it's about how our rainfall would be. And there are a couple challenges when we do the simulation of the nowcasting. And one of it is we actually have variation in rainfall. Rainfall won't just move. It actually has advection and evolution. We have 2 performances happening at the same time. Another challenge is that in different spatial and temporal changes, they are not independent. They are interrelated. We need to do them together. And another challenge is also that we need to preserve consistency across different scales. So these are the challenges that we face. And first of all, in our literature, there are 2 ways to do nowcasting. And one is called object-based nowcasting. And it actually pick up the rain cell from all the radar data. And we start to check all those rain cell who looks more like the other one before 5 minutes or after 5 minutes. And then we can have nowcasting. And this is the model that I built for UKMO. And we use the common filter way to build this model. And one thing I would like to add is actually in the past for European countries, they don't do this. And that is why we have built this model for UKMO to do the nowcasting for the afternoon shower. And we actually have quite good outcome, but it also has some challenges. So one thing is that for the afternoon shower, it won't just evac, it would also evolve. The rain cell would have evolution. And I think we all are quite familiar with afternoon shower. The rain comes so fast, and then sometimes they come really strong, and sometimes they get weak. So it actually has abundant evolution. It's very different from the monsoon. But about traditional nowcasting, we actually use computer image, or we use statistics. But evolution are quite hard to be captured in the traditional methods. So fortunately, I was able to work with UKMO and to see if we can actually leverage AI to have a better nowcasting. So actually, all of this started from one paper in atmospheric department. They actually observe what kind of process that a single core cell would face. It actually has three phases: from developing, maturing, and dissipating. So from the whole process, as you can see, there is a core in the rain cell. And the core, it will evolve in different stages. Sometimes it will grow taller. And we think this might be a very good indicator for us to know, okay, so how high it is, and then we will know when and how it's going to evolve, whether or not it will dissipate. So we actually built a simple model, and that is we bring out the rain cell from radar and to see its feature. And we have the 3D weather model, so we can do this. And actually, the whole process isn't too hard. We actually use LCM, and that is to use time sequence forecasting. So we use LSTM to predict every rain cell, how they will be evolving. And we realize AI is too powerful. A single LSTM model can actually well predict the evolution of rain cell, whether or not it's developing, maturing, or dissipating. And during the process, it can help us reduce 50% of errors at 15 minutes lead time, especially in nowcasting intensity. And this can echo with what Professor Zhang just mentioned. Actually, in many different fields, AI and traditional method, they can complement each other. If we can leverage these two methods together, we can have better outcome. And this also plays out, like I mentioned, in field-based nowcasting. It didn't pick out the rain cell. It used a series data of radar and to see how these rain field will move. Then we can have an extrapolation of the rain field. And actually, for many Met office, they all use field-based nowcasting, and it has good outcome for hydrological prediction. Object-based, they actually filter low amount of rainfall, and it's more commonly used for weather organization. And I think for the past few years, we actually have many different AI models that people are leveraging to use to predict nowcasting. And one is that AI tried to link the aversion and evolution together. And another model is they try to focus on spatial temporal feature. And we also have a lot of diffusion models lately. Sometimes the outcome that they produce sometimes are too crazy. And so let us quickly go through this model. And one is GRU, which is quite famous. Because in AI, there was a computational LSTM. It's a quite famous model that people use. And the theory behind this is that it can predict what would happen next, and it actually uses all the data nearby, all the points nearby. But it also means that we only look at certain areas. So the outcome might be blur. And rain field, sometimes they move. And GRU, they actually use this kind of new mindset. And this is what we got our observation from training GRU. And this is what we have in the early stage. And gradually, when we put in more data, we realize one thing, and that is something similar to the outcome in object-based. And that is AI appears to learn the pattern of evolution first. So in the beginning, the prediction seems the same. And then they start to learn the evasion. And then we realize AI is good at evolution, not evasion. So we know evasion is quite easy for computer to do. So from field-based and object-based, we realize one thing, and that is AI and computer, they are good at different things, so they can work together. And another model is that we actually have open source DGMR replica, and it's for everyone to use. And even for our future models that we train, we will put it online, let everybody use it. And another technology is called GAN. And why LLM is so famous, it actually leverages GAN as well. And for AI nowcasting, we actually use GAN. And so as you can see, with GAN, we can have more detail in our rain field nowcasting. And this is the development that we have for nowcasting. And in addition to that, my second point is we know AI is good at learning spatial and temporal features. So one example is creaking. Creaking is hydrological research has been used quite a lot. And that is we can use it to generate fields. So the left is what we see from radar, and in the middle, there are actually some spots. And on the right side, we use creaking to show it. So as you can see, creaking is easy to use, and it has good outcome. But it also has some limitations. And one thing is that sometimes, because we collect those data from our rain station, if our rain station did not collect those data, then creaking would have a poor prediction. Sometimes the outcome would be too smooth. Another challenge is that creaking actually predict and these photos one by one. So sometimes you can see the time sequence are not that smooth. And knowing that what AI is good at, then we actually give the photo the start for our AI and to see whether or not it could reconstruct what the actual rainfield looks like. So as you can see, all those stations only accounts for less than 1% of the rainfield. And we brought up one model, and that is we use something that we already know to give it a really blur background input. And then we use another model to give us more detail. So ultimately, we will have a more precise outcome. And that's what we have been trying to do. And once again, we got surprised by AI. AI can actually reconstruct rainfall fields. And as you can see, what our model produced is more realistic than, looks more real than crickets. And we also have further analysis, which we do not show you, but we can see the statistics performance are better. And AI is really amazing. Using a really small amount of data, it could produce and simulate rainfall. And lastly, it's about climate modeling. And we would like to know, can we teach AI to say, I don't know? And about climate modeling, what we have been doing is that we hope, because in civil engineering, we do catastrophic models. But there was a assumption in that, and that is the weather for the past 3 decades have been stable. But we all know in the previous 15 years, our weather has changed rapidly. So the data that we collected in the past 3 years may not be usable, may not be suitable for us to do the prediction. So oftentimes we ignore that our weather are now changing. And for atmospheric researcher, they use climate model, but it also has its own limitations. And like I mentioned before, AI is good at learning pattern. It's good at learning the feature of spatial and temporal feature. So this is a climate-dependent rainfall time series modeling, and that is we actually input climate variables and to see what feature are now changing the evolution. And we connect these features, put in our rainfall generator so that we can have a rainfall dynamics. So we use a simple method, it's called analog, because AI is good at finding the feature, temporal feature. So it finds the features from the data and to see whether or not that we actually have the similar feature in the past.
So we built a very simple climate disk. And it does a very simple thing. It uses a climate variable from a certain duration and to account for the spatial temporal variability and interdependence. So this model can help us extract the features, and then we can put it into the simulation. Traditionally, we will need to use a specific climate feature in a specific time. But if we use this model, it can become an outlier. And you will see that there is an unusual event. For example, we can see that there was a very extreme drought that year. And so we can see that using this model, we were able to extract that kind of unusual event. Otherwise, if we use the traditional catastrophe model, we will not be able to capture this feature. After talking about this model, how do we know if this model is correct or not? The first one is called feature importance analysis. Basically, what kind of feature have been focused on. So in which time, what feature, which variable have you paid attention to in the model? But again, That again shows us the model is physically feasible, but we don't know if the prediction is correct or not. So we try to see if we can use some kind of technique to teach AI to say, I don't know. For example, if you show AI this picture, an overconfident AI will tell that this is a dog. And that is, of course, incorrect. And we hope that our model can tell us, I think this is a dog, but I'm not sure. Because we know that the existing AI model has the overconfident problem. And so for the climate model, we also use deep learning, but it's evidential deep learning. Basically, this model will estimate the uncertainty and tells us why there is uncertainty. For example, they would say that I have never seen this data before, so I'm not really sure. So we use this model to carry out an experiment. We basically we check for overfitting. In an AI model training, overfitting means your model somehow matches your training too well. That means the accuracy will not be very good, and that is called overfitting. And that is why we put in the checkpoint. During the training phase, if the performance is really, really good and all the errors are concentrated in the same area, but when you apply other data, other test data, you will see that the AI model will tell you that there is data uncertainty. So you can see that the uncertainty will increase rapidly. And so using these kind of checkpoints, we can know if the AI model is telling us that I have not seen this data before. Of course, there are a lot of techniques and a lot of technical challenges that we have to overcome. But this is telling us that we can train our model to tell us that there is uncertainty. Finally, I'm going to give you some conclusion. We started from the physical process of rain cell to learn how to use AI to study and simulate evolution of rainfall. And you need to find the right physical features to get the right data. And secondly, we need to know what current AI models are good at, and we need to take advantage of this model. For example, they are very good at capturing spatial and temporal features, and they are very good at learning rainfall evolution, then advection. And of course, we want to pursue high model accuracy, but at the same time, for operation, it is very important for us to be able to assess models' behavior and uncertainty. So AI should be able to tell us that if it is uncertain. Thank you very much.
Thank you. Thank you to our speakers for their great insights. We will now begin a 15-minute panel discussion. So I'd like to ask the staff to assist in setting up the chairs for the oncoming panel discussion. You can scan the QR code on the screen no matter you are on site with us or joining us through our online streaming. Okay. You are welcome to ask questions, and we will reply and discuss the questions during the panel discussion. Okay, let's wait a little minute. Okay, let's welcome our moderator and panelists to the stage with a big round of applause. Let's welcome Deputy Chief Engineer, Mr. Jan. And distinguished Professor and Chief Secretary, Wei Chunrou. Our Professor Li Chouzhang. Associate Professor Li Ben Wang. Lots of applause.
Thank you very much, and thank you for staying with us. Now we will go into the panel discussion and Q&A session. So we will open the floor for participants who are on site to raise questions. If you have any question for Professor Zhang or Professor Wang, please raise your hand or post your question on Slido. AI and our experience-based used to have a lot of conflicts because a lot of times the calculation produced by AI is different from what we have learned in the past through experience. For example, we used to pay attention to the guidelines of reservoir operation, which is experience-based. For example, pre-typhoon season, pre-typhoon stage, what should you do? You should follow the guideline. And even in our Water Resources Act, we have specified the amount of water to be discharged, and also the amount of runoff. All of this are calculated manually. But today, with AI, we will need to calibrate our risk, and we need to know that the discharge could exceed our maximum peak flow, and this could lead to other risks. So when we are applying AI, we will also need to think about changing our regulations and laws because we could not follow our past experience. And we will need to. So do you have any questions?
那个 QPF 就是定量降水预报啦，定量降水预报或 ETQPF 哦，因为我们台风事件进来哦，它会逐时慢慢修正，它一开始都会给的。
Usually, when we have the pre-typhoon stage, we probably have the prediction and forecast, but the forecast will continue to be revised continuously. So I wonder, when we are forecasting rainfall, is it possible that we can have a specific or accurate forecast for specific smaller catchment area? Because usually the forecast is for typhoon, for Taiwan, the entire area, but that number could change from area to area. Is it possible that we can focus on specific catchment area for the forecast? Yes, a simple answer is yes. But we will need to find the right balance, because when we are making predictions, we should not focus too much on a small area, because you will not be able to see the entire rainfield. And if you want to have better prediction or forecast, it is better to have the whole area. But a feasible solution is to have enough benchmark. For example, we can have Taiwan's forecast as the benchmark, and then you can make adjustments according to your own catchment area. From my attempts in the past, and also in Switzerland, they have done something very similar. They use historical data plus the local features, and they compare the data between the national forecast and the local rainfall situation to make suitable adjustment for the catchment. And I think this is something you can try.
Okay, and is there any new questions? So we actually have questions posted on Slido. And one is for Professor Zhang. And that is, if we are going to introduce RNOx, so in practical implementations, what kind of challenges and difficulties would we face? In addition, are there other types of AI models that are more technically and operationally feasible? So first of all, RNOx is not a special or a hard-to-use model. Actually, LSTM is quite similar to RNOx. And if without considering feedback, BPNN is an easier one. And in practice, what kind of challenges would it have? So first one is data. Without data, AI couldn't do anything. We needed to enough amount of AI so that we can have a robust AI. And without adequate number of data, then AI couldn't do well. And that is data. And other than that, we need to have real-time data. So data scarcity is really a big problem. Let's say sometimes in the weather station, they do not provide their data. And for this part, I think we need to have more than one weather stations to give us input. So in our catchments, if one station failed to hand in their data, we still have other data handed by other station. So that's one way to do it. And with the estimated rainfall that we have and combined with the actual data collected by station, then we can have a more comprehensive data. And for the inflow, if we are now doing a short-term forecast or a nowcasting, we can use BPNN. And BPNN relies on inflow data. Without the data, it cannot predict. And if we use LSTM or RNOx, it can have a better prediction. And from my experience to predicting inflow, my suggestion is if we are going to predict P+1, P+2 forecast, it's better to use RNOx. And if we are going to predict a longer term, my suggestion is to use LSTM. So for a short-term inflow, LSTM is slow to predict. It has a greater error than RNOx. But for long-term prediction, RNOx would have more errors. So this is what we see from how these two models are behaving differently. So you need to pick one model that is more suitable for your own catchment. And next question is for Professor Wang. And that is, we have seen AI developing so fast. And do you think what kind of key competence for professional training should we focus on? Well, I think this is a rather difficult question. I think, first of all, in our team, if we wish to have a better performance, we need to learn some atmospheric lessons. And also, the technical threshold for weather nowcasting is quite high. That is why many of our students, they go to study for information technology. And they need to learn by themselves. So I think it's not easy for you to get into the field of nowcasting, because you're not just be using the models. From our experience, the models that built in UK is not suitable for us to use in Taiwan. So I think we need to learn atmospheric knowledge. Then we would know what kind of situation that we will have, and we need to put it in our models. And I think you need to have a great IT competency so that you will learn these models fast. And you need to have abundant knowledge in meteorology and hydrology in many different disciplines. And I think another aspect is your department would have to support you. And that's because in our department, we don't have too many required lessons. We actually barely have required lessons. So our students have time to learn other courses. Yes, I think for meteor hydrology, this is quite a difficult subject. And when I was finishing my master thesis, two of my advisory professors, they were really good, and they all major in meteorology. And they were all really distinguished professors. One is Professor Wang, and the other one is Professor Xu. And these were what I have as my advisory professor 4 decades ago. And I still remember that day when these 4 professors fought with each other. And they are like, you can't even make a precise prediction. Can you make it more precise? And for our meteorology professor, he said, of course, we would have some changes. The real situation is always different, and we have different scales. We have convective rain, typhoon rain, everything are all variables. So I think in different domains, it's really hard for us to predict, to produce a precise outcome.
Our next question is for Professor Zhang. When we face intensive rain or rapid change of runoffs, what technology or what method can help to improve the accuracy of flood forecasting? I can only give you a simple answer. Usually, we face torrential rain or intense rainfall. But on the other hand, we still need to use the AI model. From our experience, we cannot put in all rainfall events because you need to know you are training AI for a specific purpose. Do you include all rainfall events, or do you want to focus on major rainfall events? So I already talked about this earlier. I had a student who focused on the pre-typhoon stage, and also I have AI for the post-typhoon stage. So you need to know what you want to train AI for. For example, if you want to focus on peak flow over 3,000 millimeter, then you need to focus on all those events and ignore all the others, because you want to focus on peak flow with over 3,000 millimeter. So floods with peak flow lower than 500 are ignored. So you can have the total rainfall over 200, and then you can have better training for AI, but you can ignore regular rainfall events because you want to train AI for a specific purpose. Our next question is Professor Wang. In southern Taiwan, we could face the problem of monsoon and torrential rain in southern Taiwan. So can you use AI to explain or to improve nowcasting? Basically, there are two steps involved. The first step is called initiation. It started to generate, and then so when you have a storm, you need to get enough rain or enough water for it to become a rain cell, and then it will be picked up by radar. For meteorological or weather expert, it's very difficult to predict where there will be a rain cell, because the temperature, the humidity, and the local features will all affect the production of the rain cell. If you do not have any other information, it is very difficult for us to get the convective cell. And it's not something we can do even with AI. And for radar, we can use the local features to make predictions, but the likelihood of us knowing where there will be a rain cell is very low. And of course, we still need to continue to study the advection and as well as the evolution of rain cell. The production of the rain cell is still something that is very challenging. At present, we can use satellite image, and we also have these geostationary images that are available. These can help us improve our observation and to observe the changes of humidity. And then we can perhaps have a 15-minute lead time to predict that there will be an afternoon shower here. So the atmospheric forecast would say that this afternoon at around which time it is very likely that which area would have shower. And then we can use the satellite image to check if it's true. And then finally, when there is a rain cell, the radar can pick it up. And I, at present, focus on only 2 stages. I haven't been able to connect all 3 because usually the rain cell just suddenly appear. Again, evolution is very important for rain cells, but it's very difficult for us to predict when a rain cell will appear. The weather radar has its limitations. In fact, Taiwan has started to work for the flood forecast, and we already wanted to have the rainfall radar, because in the past our focus is weather radar. But the rainfall radar is about only 15 degrees. So it's very different from the meteorological radar. And meteorological radar will need to also get the information of wind and the wind direction, but the rainfall radar focus on rainfall intensity. But the Japanese advised that we can install the rainfall radar, but unfortunately, the central authorities was not interested. Now, our Water Resources Agency is working together with our Central Weather Bureau for the rainfall radar. And at present, our rainfall forecast continue to use the radar for the prediction. And another question for Professor Wang. When we are training our professionals from the angle of innovation, what kind of challenges will we face? And also, what should the government or schools do to facilitate the application or to facilitate innovation? I was very lucky to participate in a very big EU project, RAINCAN. And that's when I started to use a lot of data from the rainfall station and rainfall radar. But whenever we had workshop, we will put the weather experts together with the hydrology experts, because if we want to collaborate, we need to know what each other need. For people who focus on urban hydrology, we want to get higher resolution, but the weather expert will say it's not possible. So we will need to carry out the data analysis. We will see that actually spatial is more important than temporal. And so we can then have long pulse and short pulse signal, because the long pulse signal takes more time, but it will be more accurate, and the short pulse will be faster, but it's not that accurate. So the Water Resources Bureau and the Central Weather Bureau are talking to each other, and we are also talking about what each other need. And we are using AI to try to bridge the gap. This is what I did for the data integration, because our observation at the atmospheric level would be very different from the ground level. And we need to know each other's need in order to really help each other. And for cultivation of talents, cross-disciplinary is a very important concept. We can probably invite our hydrological experts to go into IT field, and it would be easier that way, because the IT experts would not be that interested in hydrology, and their salaries are usually too high for them to change field. But if you are someone who loves self-learning, you can also see great advance and great progress if you learn it by yourself. Because we know the step-by-step and all the stages of hydrology. And so if you are running or writing a computer program with AI, it would be much easier compared with a computer scientist who knows nothing about hydrology. So, for example, our American expert Cameron is really good at checking if this data or if this observation makes sense, because he's the expert in hydrology. And so I think this is something that we can do for talent training.
Yes. And we have 3 more questions. Next question is for Professor Zhang. You have done a lot of practical projects. And have you found that AI is actually not good at? And we still need to train AI. Well, I think just like Professor Wang just mentioned. And I think I have the right, just like AI does have their own right, to say, I don't know. I think for many projects that I have done, AI keeps improving. And why does it need to improve? It's because we still have a lot of problems unsolved. And Professor Wang mentioned about one thing that is interesting to me, and that is after using AI, we know AI always answer. Sometimes they give us wrong answer. That's because that's how we train them. We train AI to answer. So even if they see a fox, sometimes they will tell you it's a dog. So I think for the challenges that we are facing now, there are some challenges that AI cannot solve. Not even we're now having GAN. And I also do a lot of city flooding. And if we can implement GAN into it, we can make it more precise. So when having a new AI model or tools, then we can start to think whether this new tool can help us better solve our problems. And actually use one in a new project, and that is to use transformer to predict the inflow and the downstream flow in the groundwater in Zhuoshui River. And now, these models, they can talk to each other. So whenever we have new AI tools, we can start to think whether this can solve our problem. And if not, let's wait. I don't have a special answer to that. And I think this question can combine with the questions posed to Professor Wang, and that is, we can use AI to predict where might face flood. And now, when we are doing the flood prediction, we have the warning, and that is to use the data that actually happened and to point out which region might face flood. And next question is also for Professor Wang. So about the rain observation, what can we still improve? I think, first of all, for AI nowcasting perspective, so far for our Weather Bureau, in their 10 minutes weather forecast data, it's hard for our AI model because UKMO can actually predict a 5 minutes data. And with the 5-minute data, it trains the AI model that we cannot train to have with the 10 minutes data that we have. What we've seen from the model trained by Google, they actually feed atmospheric data to their AI. And I think for our AI model, if we only have 2 pictures or data that have 10 minutes difference, the continuity is bad. So our AI would have sometimes to struggle. And I think we need to have a better time resolution so that we can train our AI more easily. And it's the improvement that we can have. Another thing is for our rain station and the data that you provide. The data needs to be more precise, and in time resolution, it also needs improvement. Because I actually our department gave me a lot of budget, and I have set up a lot of rain station. I have different types of rain station, and I try them out. And I think for operation, I think for our weather bureau, they get prepared for typhoon, and the tools that they have can only produce low resolution outcome, and the rain data that they produce, they cannot perform to predict a shorter time prediction. But if you want to make them to predict like 1 hour prediction, they can do it. But in Taiwan, we have a really high rain intensity. So for our tipping bucket, it's not easy for our tool to predict a short-term rainfall if that's too intense. And I think for our traditional rain station, it didn't do too good. But now, after we have our comparison, it can actually supplement with new method. And for the weight bucket, the way the EU has designed it, they only need to get the water out every 30 minutes. And I think for the weight bucket, it cannot measure rainfall that's below 0.1 millimeter. And the last one is laser. So comparing these different tools, when they are all performing well, they are quite consistent. And for the laser one, requires less maintenance. And I think for Taiwan, we can have new tool that might be expensive but require less maintenance. And if we're gonna do a better urban flooding prediction, time is key. And I think a lot of tools that we have in our rain station are not designed for urban flooding prediction. Thank you, Professor Wang. And next question is, when we are using AI in short-term weather forecasting, how should we view the importance of model uncertainty and interpretability? And I think nowadays for mainstream AI models, they all go after one thing, and that is accuracy, which I think is tricky because no matter what kind of AI model you have, the most important thing is what kind of data that you input, that you feed the AI. If you want to make the AI predict a better outcome for a massive rainfall event, you need to feed it with related data. Oh yeah, and also for the uncertainty, because AI is data-driven, sometimes you have to look back to see if the outcome is correct. Sometimes AI will produce something that's against physics, which is bad for the future development for AI. Because if it's against the rule of physics, it will produce an absurd outcome. And if it somehow can reconstruct a physical reality, and whether or not it actually sees the data, if the outcome is good, I think it's good. And lastly, we need to start to invest in new AI models that can help us to see whether or not our outcome is good or not. And this is for our decision makers. So the AI model can actually tell us that I have not experienced this type of event. And for our decision maker to make decision. And if AI can tell our decision makers that I actually seen this kind of data in the past, then our decision maker can be more confident in trusting AI. And this is a key for AI to be actually implemented for our decision maker.
Our last question is for Professor Zhang. The surface runoff coefficient is also an important factor affecting river flow prediction at the dry season and the rainy season. So has your study considered this into your AI model? Yes. We think about runoff coefficient very often, but we don't really know the actual runoff coefficient value in the field. A lot of times our calculation is wrong, and we do not have a one-size-fits-all runoff coefficient. For example, you already mentioned that there is difference during the dry season and the rainy season, or perhaps you experience a long dry season and then you have the rain. So we all try to get the real-time data on groundwater because we know that the groundwater level will be affected by rainfall. So perhaps if we can get real-time groundwater data, we can then know the overall situation of a catchment area. If this catchment area has groundwater and the groundwater level is low, most of the rainfall will go into the groundwater. And so the runoff coefficient will not be that accurate. But if the groundwater level is high and the rainfall will not go into the groundwater, then the runoff will increase. So if we want to have accurate forecasts, it is very possible that we will underestimate the recession, even though it's for the same rainfall and with the same amount of water. You still have variations because the groundwater level would be different and the soil would be very different. So we will need to put that into account. But when we put the storage function model, we see that actually it can produce very accurate prediction. Unfortunately, for the soil, it is very difficult for us to determine the dryness of the soil. But maybe we can observe the accumulation of water in certain area if that area has experienced drought for a long time. Then we can work to improve the AI model's accuracy. Otherwise, if we just focus on drought or focus on areas that have experienced rainfall, the number and the prediction will still be wrong. Indeed, we need to count both groundwater and surface. I thought that I don't need to talk at all, but I got a surprise. As Professor Zhang mentioned, we need to take into account the groundwater level. And our present data are quite fast. Usually the data is updated every 10 minutes. And also the WRA is focused on land subsidence. So to prevent land subsidence, we have real-time monitoring device so that we get the sensor and get the sensor data in real time. Thanks to technology advancement, we can get this data. I am not someone who is involved in AI projects, but because I work a lot in projects related to groundwater. And so we still need to rely on the physical patterns to train the AI models. So I'm working with University of Stanford to use the data and to train the AI. And we talk about land subsidence and also the K value. We are also accounting all the other flexibility coefficient. Technologically speaking, we are getting closer. But what I wanted to add that what is my view of the future challenge related to AI. In AI, there are three important components. One is data. You need to have sovereign data. Every place has different disasters. You need to have your own sovereign data. And I believe that our authorities is doing very well. The WRA has done a lot to accumulate relevant data. And they have stored a lot of data related to groundwater level, also the reservoir safety. They have all accumulated a lot of sovereign data. The second component is the computing capacity, and this is not something that is beyond our control. NVIDIA and AMD is involved, and their computer can be less than 100,000 NT dollars. You can get subsidy to get these AI computer from NVIDIA. And the third one is algorithm. As Professor Wang and Professor Zhang already mentioned, you need to have algorithms that are supported by physical features. And what I can only see is the water resources area. I was involved in the examination committee for the civil engineering discipline, and usually we want to recruit 75 civil engineers, but we cannot get enough talent. So during a big forum, I actually invited the examination committee's staff to help me organize all the data related to the talents of civil engineering. And we know that we see a big gap of over 3,000 engineers. Yesterday, one of our speakers also mentioned that the WRA is having difficulty finding enough professionals who can help them solve water-related problems. And also in our field, we have two classes, and a lot of times a lot of students would transfer to other departments. So the Ministry of Examination is talking to me about how we can promote the discipline. Our government is very efficient because we have a lot of you who are high-level engineers, who are also civil servants. But now we are not finding enough high-level engineers who are willing to become civil servants in the government. I believe that a lot of them decided to work for TSMC. And they were usually very happy working for these high-tech companies because their salaries are really high. But for us, in the water resources field to develop AI, we need more talents to train AI for the water resources area, we need high-level talents. So indeed, this is the challenge that I see. Thank you.
I think for AI, we need computation and algorithm. In computation, we need to have a good computer. And for algorithm, we need to have talents to come up with new algorithms so that our computer can compute for us. And we also need data. So is there any question? And I think we have been talking about the uncertainty in many different fields, about the rainfall, about weather. And I think in the 1990s, one of the prosecutors was called upon to the court to explain why the rainfall forecast was not accurate. You can imagine that, right? And I told them for flood prediction, oftentimes it's not accurate, but it's not wrong. So is there any question? In the interest of time, and if we don't have further questions online, then I would like to thank you. I would like to thank our today's field experts for their insights. And is there anything? Okay. Yes, I have something to say. We have souvenir for our speakers. So let's invite our Deputy Chief Engineer, Mr. Jian. And so, for our guest today, let us have a little ceremony. And everybody move closer. Okay. Everyone has your own share. Let's have a big hand for them.
Your 爱心，爱心好不好？可以吗？可以吗？会比爱心啊？可以，1、2、3，耶 ！1、2、3，smile。Thank you， 谢谢，谢谢，谢谢我们署内的长官，还有我们今天的讲者朋友们。好的，也非常的谢谢我们现场所有朋友今天的参与。
Thank you for your participation today, and please remember, don't forget everything that you brought here today, and please return the interpreting machine. And this would be the end of our today's forum. Thank you for participating.